Hello, student. Welcome to our new lecture, which is regarding lecture 14 and 15. Inshallah, in this lecture, we are going to discuss electrical DC generator. We are going to outline an introduction about DC generators. We will see the working principle of a DC generator. We are going to introduce slip rings and brushes. We will see how we can get a DC current by using a commutator. We will show you some types of DC generators, and we will see together, inshallah, two types of DC generators, which are separately excited, and shunt self-excited DC generators. Now, how do power stations provide electricity to thousands of houses around the city? Imagine that in one station in electrical company in Saudi Arabia, which is Skiko, can provide power to all, let's say, Jubail citizens. Okay, so they don't use giant batteries, of course. They will they do that by spinning a giant turbine. So this turbine is going to be attached with the generator. So we will have a movement from the turbine, then generate this generator is going to generate us power. Okay, so the prime mover could be steam, right? So steam is going to revolve the shaft of the turbine, and this shaft is attached to a generator shaft, and the generator is going to have a voltage output, and this voltage can be transferred to any load. Okay, so it can be the prime mover can be steam, can be energy of falling water, which is hydraulic, can be wind turbine or electrical motors. Okay, we will focus on the inshallah DC generators in this chapter. Okay, how does turning something create electricity? And this is a very core question for our lecture today, inshallah. So I said earlier that if I need to have a voltage, then we need to move something, right? So this technology is based on electromagnetic induction discovered by Michael Faraday more than 2000 years ago. The basic idea, if we have three elements, ya shabab, if we have three elements, which is coil, okay? When I say coil, means there is a number of turns, right? Number of turns. Second thing is movement, right? By up, down, or clockwise or anti-clockwise. And we have a magnetic field. So if we have those three factors, sorry, we will have an output voltage. Okay, we will have an output voltage. So all we have to do is attach a coil of wire to these giant turbines and place them inside the magnetic field, So we will have a coil and movement from the turbines and a magnetic field. So a turbine rotates, the coil starts rotating and moving up and down inside the magnetic field that produces an output voltage. Okay. Now, in the left side of your screen, the left side is representing a magnetic field which is always going from the north to the south, right? This is a concept, okay, shabab? So always the magnetic field is going from the north to the south, from the north to the south, okay? Sorry, I want to check if the mic is working. Now, if we have a metallic bar, okay, it is not moving. In the left side, it is not moving. In the right side, okay, figure 1.2, we will have this bar is moving, is cutting the magnetic field lines, right? And if it is cut the magnetic field up and down, and continuous movement, we will have what? We will have electricity. Okay. And this is a basic concept. Okay. Now in these pictures يا شباب, we are going to introduce a coil, right? So as you can see here, if I can write something here, this is a coil. As you can see, this is a coil. Okay, this is one coil. We have two terminals, right? So in this type, in this time, the coil is horizontal, right? And this time here, the coil is vertical. But you can see that the pink color here is upright, and here is down. So it is rotated. The we will have rotation, and we will see what is the difference if the coil is up or down. Okay, we will see the movement of the current, everything, inshallah. We will see, and I will explain everything. But make sure that you need to know that we have a coil like this. We will have a magnetic field, and we will have what? We will have movement, we will have movement. Okay, now the working principle of TC generators. How do we figure out that the direction of the induced current? Shabab, we already know from physics. We have already you have already seen the right hand rule, right? So we will I will just give you a hint or revision little bit about the right hand rule, which is very important to know the direction of the current. Okay, so we have already learned something called Fleming's right hand generator rule, which says that when you stretch the fingers of your right hand, okay, as it looks in the finger, in the figure next slide. Okay, the thumb represent the thumb يا شباب, the thumb represent what? The motion of the coil. Okay, the forefinger, okay, اللي سباب يا شباب, gives you the direction of the magnetic field flux. Then the middle finger gives you the direction of what? Of the induced current. We have three directions يا شباب. The thumb is for the coil movement, is it up or down? The forefinger sababa gives you the direction of the flux, okay, which is always coming from the north to the south. The third one is the middle finger gives you the direction of the current. Okay, so if the coil is moving upward, the induced current will be into the screen. Okay, if the coil is moving downwards, the induced current will be out of the screen, and you can, inshallah, in the coming pictures, you can see the and you can try at home the right hand rule. Okay, so every time the coil, when it is perpendicular to the magnetic field flux direction, you will see that the current direction will flip. Okay, let us see it together. Okay, shabab, so let us focus on figure 2.7 in the middle one. Okay, so in this time, and this is the coil, right? As we explained before, this is the coil, and as you can see, this is the forefinger, and it is representing what? The direction of what? Of the magnetic field, which is coming from north to south, north to south. Okay, let me delete this one. Okay, now for this finger, which is the thumb finger, it represents what, ya shabab? Represent the movement of coil. The coil is going up, right? As you can see, the coil is going up. What about the middle finger? The middle finger is representing that the current is going like this, ya shabab. Let me just throw it okay, like this. Okay, the current now is like this. Now, as you can see here, shabab, current now is like this. Okay, for the pink wire, right? But for the blue wire, the current is going like this, because this is the middle finger. Okay, and this is the direction of the magnetic field. And now, as you can see, the thumb is representing the coil, which is going down. So we have going up and going down. and using the right hand rule, you will see that there is a current going in this side in the upper part of the coil, and we have current going down in the lower part of the coil. So this is the direction. As you can see, we will have a plus minus يا شباب, huh? This is plus and this is minus. Okay, so we will have plus minus, so we will generate AC. Okay, but remember, now we will talk about the DC generators, right? So the direction of current must be at the same direction, right? Direction of current in DC, it is direct current, which is always constant. So we will see inshallah in the coming slide inshallah. So make sure that you know the pink color here, the pink color, which is the upper side of the winding, is going up, and the yellow is representing the lower part of the coil, which is going down. So now we will have a magnetic field, and we will have movement, and we will have what? Coil. Then we will generate an AC current. Okay, this is AC current. Now as we explained that the pink wire here is going up, direction of the current is into the screen. If you use the right hand rule, you will see that the middle finger is in this side here, right? And the thumb is like this, so it is going up, right? It's representing the coil is going up. Now as you can see here, now the angle is almost 180, right? Right, it's almost 180. What if the angle is after 180 in this side? So can you see that? Can you see if we have can you see the direction of the current here? So here the direction of the current is like this, the pink wire. Okay, this is the direction current. Now the pink wire is in the other direction. Why is that? Because once we reach 120 degree, the direction of the current is going to be reversed. Okay, so it will go the other way around. Okay, the other way around, and it is the same for the lower part, which is this is up and here is down. خلاص, we need to see that if we rotate the coil in some angles, we will see that the current is going up, and some angles we will see the current is going down. خلاص يا شباب, inshallah it will be clear. Now what will happen when we connect or when you connect your coil to an external circuit? As we explained, we have two coils, right شباب? This is one coil, right? So this is one coil with one terminal, one coil with with two terminals, right? So I have this one and this one. What happened if I connect it to a lamp? Okay, so we will see together what will happen. Now as the coil is rotating, notice that the wires start twisting, tangling and turning. So to avoid, we will use an arrangement involving brushes and slip rings. Okay, basically we have two metallic rings. Inshallah I will show you on the coming slide. Each ring is connected to one coil only by the carbon brush. Okay, the brushes is basically يا شباب is basically a carbon brush that absorbs the current, okay, are fixed, not rotating. Let us see together inshallah. So this is the lamp. Okay, now we connect it to this terminal, right? And as you can see, now we have movement here, and the coils are twisting, shabab. And this is the problem. The coil will the wires will be what? Will be cut, right? That's why we will have two metallic rings, which is made of copper, right? So we don't have now twisting problem, and the brushes are fixed, not moving, huh? So the ring is moving, but the brush is not moving. That's why we don't have problem. So now I explained for you the slip rings and brushes. What is the importance of a slip ring and what is the importance of brushes? The brushes is going to absorb the current. The slip rings is going to avoid twisting of the wires. Okay. Now, in this figure also, we will see the direction of the current. This is going up now, and here is going down after 180 degree. Okay. Now, as you can see here, Shabab, this is our coil. Okay. These are the poles, north, south. Okay. These are the brushes, and these are the rings, slip rings. Okay. This is the load. Now, once this coil is 90 degree, this is 90 degree, right? This is the magnetic field here. This is the magnetic field. And the coil is now is 90 degree. 90 degree, that means that we have a maximum voltage. Maximum voltage. Why is that? Because the cross-section area, as you can see, the cross-section area of the coil is covered by all the magnetic field that it can cover, right? So if we have the coil in this way, okay, and this is the and our poles, okay. So in this direction, we don't have what the cross-section area will not be covered for all the magnetic field, right? So it is going to be dropped until it goes what, zero. Zero when it reaches 180 degree. Okay, then it is when you reverse direction, the current will be reversed until it is going to the 90 degree, and which is reach the maximum negative voltage or negative current if you want, and it will go to zero and so on. So we will have an AC current and AC induced voltage. Okay. Now, if you want to build a DC generator, and this is the critical part here, يا شباب, we where we don't want the current direction to change. نبغى نفس اتجاه الكرنت. We want it to remain the same direction. Okay. We can do that by attaching split rings. Okay. It is a ring that is split in between, giving two half rings with some gap between. By using the split rings, the induced current going to the bulb is one direction DC. Okay, well, let us see together. This is our, in your left side, this is our combination of coil, magnetic field, and movement, right? And now we introduce you to split ring. Split rings means I have ring, but it is split in half, right? So we will have open circuit here, right? So as you can see here, now the pink color here is like this, right? So the direction of the current here like this, and the direction of current here for the blue is here, right? Now, if this brush, if this one is moved, let us see the next slide. Please, Shabab, check the video for more understanding. Okay. Now, this is our slip ring, okay, and sorry, split ring, which is commutator. And as you can see here, Shabab, now the pink here, Shabab, the pink is in this direction, right, up, and the yellow is down. Now, once we have a movement, and can you see the brush here? The brush now is going to have an open circuit. We don't have current, right? So now the pink wire is going to be in this side down, right? But it is open circuit. So the direction will not be changed. The direction will not be changed, right? Because we have open circuit. So as you can see, the direction will not change because of what? Because of the split ring. Because of the split ring. As you can see here, this is the yellow, and we have a movement. then the the current is going here up, right? It is like this one. Let me just do it again. Although the current here changes, okay, although the current here changes, but there is an open circuit, okay, we will have the same now. Now we will get the yellow, the blue wire, which is the same angle as this one, the same direction. So because of this open circuit, we will have same direction current. So as you can see, we will have just only the positive cycle, right? So if you have a lamp, it will go on and off, on and off, on and off, right? Because off means 0, on here. So we will have on, off, on, off. And this is not pure DC. This is not pure DC because we have problem with the lamp, which is on, off. We need to keep the lamp is always on, right? DC current, with DC current. So returning to the DC generator, we can improve the pulsing DC voltage by using 4 coils. So if you increase the coils, number of coils, then we will have small ripple, okay? And this will give you and if you increase the number of coils, then we will have a DC current, pure DC current, pure DC current, okay? So it is before it was like this, and then it was we remove this one, it will be here, right? And then we increase the number of the coils, and we would have, okay, okay, so we will take this one only, the upper one, until it reaches to this shape. خلاص يا شباب, this is very smooth DC voltage. To sum up, please try to read this slide. And the direction of the current depends on whether the coil is going up or down. And we have split rings, we call it commutator, and it keeps changing the contact for every half rotation and make sure that the current does not change. And this is very clever idea. So to have a DC current, it is very clever to split only the rings by half, and the current will be in one direction. Please see the video that I attached, okay, the link, so that you can see a better understanding, okay? So the rotation of the coil increases, the magnetic field increases, the output voltage can be increased by the rotation of the coil and the magnetic field, okay? So this is the construction of a DC machine. Okay, a DC machine. It has a stator. This is the stator. It has inside a field winding. Okay, and we have a rotor, and this is called a rotor. We have rotor windings, and we have a commutator. As you can see here, we have many windings, okay, for the commutators, and then we have a DC current, okay? So the types of DC machines, DC generators, okay, we have two main types, which are separately excited DC generators. We will have armature winding, and we have field winding, and this field winding is supplied by a battery, okay, by a battery. Okay, the second type, which is self-excited DC generators, we will concentrate on the shunt, which is the field is in parallel with the armature, and series, if you have time, the field is in series with the armature, and we have combined and have two types of combined, so no need to understand. So we will explain just only the separately excited and shunt self-excited DC generators. Now, for the separately excited, as I explained, we have two poles, right? North representing north and south. Okay, so those poles is representing the field winding. Huh? This is very important. When we talk about the field, that means that we have poles north and south. خلاص يا شباب. When we talk about the armature, this is the output voltage. This is the induced voltage. Okay, where the induced voltage is located. خلاص. The field winding is for the poles north and south, and this armature winding is for the induced voltage. خلاص. So the field winding is supplied by a battery. Okay, and the armature is we will have a movement here for the rotor, and this is called armature winding, and we will have an output voltage here. خلاص. And please try to read this to understand. So the generator is said to be separately excited, means that we have a DC connected terminal to AB causes an exciting current to flow. So we will have an exciting current. What do I mean by exciting current? Exciting current means تحفيز محفز. current يحفز ايش؟ يحفز البولز عشان يصير عندك نورث وساوث يا شباب، فلازم في current يحفز البولز، ولا يا شباب؟ يحفز المagnetic field عشان يصير عندك magnetic field. If we need to have a magnetic field in the poles, we need a current, right? This current is going to, if you have a coil, is going to generate a magnetic field, right? So we need a battery, external battery, to have an exciting current for the field winding, okay? In the field winding also, we have something we call it rheostat. Rheostat means it is variable resistance, and this one is very important to control the field current. If we control the field current, okay, we are going to increase, if we, let's say, increase the field current, we are going to increase the magnetic field, we are going to increase the output voltage, so we control the flux in the poles, and hence we control the induced voltage. Okay, RFW, which is resistance field winding, is the resistance of the field winding. On the other hand, the armature, we have resistance which is called RA. Inshallah, we will see it in the coming slides. Okay, now we will introduce to you a very important terminology, which is armature reaction. What is armature reaction, shabab? Armature reaction, we know the poles now of the machine, we know the magnetic field, right, of the field winding, and the armature winding, right? We have two fields, right, for the armature winding, and which is the rotor, and the field winding, which is the stator. So if we have a load, right, we will have a current in the armature winding, so then we will have a magnetic field. So if you have a magnetic field that interacts with the armature field, then the effect of we will have an armature reaction, which is some losses occurs. So as it is says, this sentence says, the effect of armature flux on the main field flux is known as the armature reaction. So the armature reaction is the effect of the armature flux on the field flux. That's it. خلاص. Now, what will happen if we have an armature reaction? The armature reaction is going to distort the main field by weakening the main flux. Okay, the main flux, it will be weakened. Okay, weakened. So the armature reaction is going to distort the main field, and it is going to weaken the main flux, which is the field flux. Now let us see the separately excited characteristics. Now this is the field winding, the field current, okay, against the flux. Okay, so we have a formula, and it is well known, which is induced voltage. Induced voltage, huh? You know, induced voltage is K multiplied. This is constant multiplied flux. Okay, so if we increase the flux means magnetic field, huh? If we increase the magnetic field, the output voltage will be increased, and this is very important. خلاص. Now, if we increase the field flux, the field current, we are going to what? To increase the flux. If we increase the flux, we increase the voltage. So as the current of the field is increased, we will have what? We will have a more voltage. But remember that as you can see, let me just erase this one. Okay. Remember something. The flux for the balls is going to be saturated, means it is going to be at full position. يعني لازم يعني تكون مثلا البولز هذه تكون ايش؟ مشبعة بالماجنتيك فيلد، مشبعة. اوكي، مشبعة بالماجنتيك فيلد، ما تقدر تزيد مهما زودت الفلكس، مهما زودت الكرنت حق الفيلد راح تكون ساتشر. ليش؟ لو تلاحظون الكيرف هنا يا شباب من 0 الى 1 امبير. اوكي، من 0 الى 1 امبير الكرنت، الفلكس قاعد يزيد which is the voltage، صح؟ الفلكس قاعد يزيد. بس انا زودت من 1 الى 2 امبير، يعني 1 امبير زياده، وشوف الزياده قليله جدا، الزياده قليله جدا. ومن 2 الى 3 ولا زالت زياده قليله جدا، الين توصل مرحله انه ما عاد يقدر يزيد. ف once the poles are saturated, then the effect of the field current is going to be nothing. It's going to be nothing. خلاص. Now the separately excited at no load and at load. So at no load we will this is the armature, okay, and this is the resistance of what? Of the armature. So that's why we call it RA. This resistance is inside, is inside. But this is the equivalent circuit. This is the if I ask you about the equivalent circuit of separately excited DC generator, you will draw this circuit يا شباب. You will draw this circuit. خلاص. At no load. This is at no load. At no load, the means that we don't have current, so IA is 0, and VT is equal to, this is the VT, V terminal, V terminal is connected to it's going to be connected to load, so we don't have load here. So these terminals, V terminal is equal to E node, okay, because we don't have current, that's why there is no voltage drop. Then they are equal, okay شباب. And in the field winding, is sourced by a DC source, and this is the field winding, and this is the resistance of the field winding, and this is the rheostat, so we can change the current of the field. Now at load, that means that IA is equal to I load, right? And if you have a variable load, okay, here, so we will have formulas that means that VT is equal to EA minus the drop, which is IA multiply RA, minus the drop here, the resistance, right? If we have a winding coil, then we will have resistance, right? And this resistance is if we have current, then we will multiply together. This is voltage drop. This is the voltage drop. This is by KVL, Kirchhoff voltage law. Now for the characteristics of DC separately excited at no load, we can see here that after the poles get saturated, even if we increase the field current, the flux will remain constant, so that the output induced voltage will be constant. So this is the field current, and this is the output voltage. Because we don't have current, because we don't have load, we still increasing the current until, so as you can see here, it is saturated, so we cannot increase anything. If we increase the current, we are going to burn the winding of the field, and the output voltage will not change. So we need a small current. The field current is always by milliampere. The field current is going just only, that is why it is called exciting current. Exciting current means محفز، فنحتاج بس current بسيط عشان يشغل لي، عشان يعطيني magnetic field. اوكي، فعشان كده احنا نحتاج الكرنت البسيط هذا. فمهما زودت الكرنت راح يوصل لحد معين اللي هو يكون البول يكون مشبع بالماجنتيك فيلد، فما يقدر يزيد اكثر. خلاص اوكي، ان شاء الله تكون واضح. now this an internal characteristics curve shows that when we have when I say شباب EA, I mean that we have a load. When I say E node, that means in case we don't have load. And this is the voltage drop of the armature reaction. So if we have EA is equal, now EA is equal E node minus voltage drop of the armature, of course, because we said that in case of on load characteristics, on load generated voltage, we have an armature current, and this will cause armature reaction for us. So the armature reaction is going to be there if we have a load. If we have a load, we will have an armature reaction because of the current. خلاص, this is very important يا شباب. So EA is equal to E node, which is bigger. E node is bigger than EA, right? So EA is equal E node minus the voltage drop of the armature reaction. Then we have generated voltage. Now, the external characteristic curve shows that the relation between the terminal voltage VT. So the VT now it is which is the points where we connect the load. So VT is equal to EA minus IA RA, which is already explained. The voltage drop on the resistance of the armature. Of course, this is Kirchhoff voltage law, and you should know it, Kirchhoff voltage law from circuit 1. And this is already explained. Can you see يا شباب here? Now, if there is no armature reaction, this is very important characteristics graph here يا شباب. If there is no armature reaction and armature voltage drop, يعني السيستم عندك تمام، اوكي، ما عندك مشاكل armature reaction ولا عندك مشكلة voltage drop. Okay, the voltage will remain constant for any load current. So the straight line AB is representing the no load voltage E node versus the IL. So this is AB curve, and if you don't have problem, then we will have a straight line, and this is will not happen. Of course we have armature reaction, of course we have ohmic voltage drop, which is the resistance voltage drop. So this is an ideal case. This is an ideal case, okay? AB. Now, for the second one, due to the effect of armature reaction, okay, the on-load generated EMF EA is less than the no-load voltage. You know, of course, because we have armature. Can you see? This is the straight line, and this is the ideal line. If we have an armature reaction, this voltage is going to be dropped. Right? So this is the drop of the armature reaction. And the third one is the voltage term is less than the EA, okay, due to what? The voltage drop. As you can see, if we have voltage drop, and we will have this is ohmic voltage drop, okay. So this is called the external characteristics, and this is called the internal characteristics. So internal characteristics for armature reaction, and external for armature reaction plus voltage drop, plus the voltage drop. This is the real one. This is the real one. Okay. For the shunt generator, it is very clear and from this picture that the field winding here يا شباب, as you can see, it is in parallel. Okay, in parallel. As you can see, this is the armature winding, and this is the field winding. So they are in parallel. Okay. Now we have a problem here. We don't have battery, right? So how can we get the field current? Okay, we said that we have three factors to generate voltage, right? The factor number one is the coil. Factor number two is the movement. Factor number three, which is magnetic field. Now, how can we get the magnetic field from the field now? We don't have current, right? And then if we don't have current, we don't have magnetic field. Now, how can we get the magnetic field here? There is very important terminology you should know, which is residual flux. Residual flux. Residual flux means we have small flux in this coil from previous usage. يعني عندنا فلكس قليل موجود من استخدام المسبق، فيبقى فلكس في الكويل نفسه. الكويل نفسه يبقى فلكس قليل. طيب كيف يزيد الفلكس هذا؟ إذا كان عندي أنا موفمنت هنا، فراح يكون عندي كارنت، رايت؟ الكارنت هذا راح يتقسم، يروح على الفيلد شوي ويحفز لك الماجنتيك فيلد الموجود هنا اللي هو ريزيدوال فلكس، ويحفزه ويزيده شوي. طيب هل الكارنت بيزيد زيادة؟ لا، الكارنت بيزيد على حسب الكارنت المسموح في الوايندنج. اوكي، الوايندنج هذه مصممة على تستخدم كارنت بالملي امبير، فخلاص ما راح تزيد عن ملي امبير. بس بسبب الريزيدوال فلكس اللي هنا، الكارنت اللي هنا ساعدنا انه يمر كارنت في الوايندنج. Then we will have a field flux. Okay, this is very important and I think it is clear. Now the load is also connected in parallel across the armature. The shunt field winding has more number of turns of thin wire. That means less, that means high resistance, which is thin wire. Okay, therefore a small amount of current flows through the field, a small current, okay, in milliampere. Rheostat, of course, it is connected in series with the field winding so that we can control the field current. Therefore, the flux can be controlled. Therefore, the terminal voltage can be controlled. And this is the terminal voltage formula, which is VT is equal to EA minus IA RA, which is the voltage drop. The field current is IF, right? A field current, which is equal to VT divided by RFW, which is resistance of the field winding, which is clear. Armature current IA is equal to IL plus IF, because the armature, all are in parallel, so it will be divided for the load, and sum of the current is going to the field. Power developed by the armature, so BA is equal to EA IA, which is current multiplied voltage. This is very clear. Power developed to the load, B load, which is VT multiply IL. Okay. Now this is the characteristics of the and this is the equivalent circuit of the shunt self-excited DC generators. This is at no load. At no load we don't have current here, high load, right? But we have, if we have movement here, then we will have current going, small current going to the field, right? And we don't have current here because we have a voltage. So this voltage is going to be the same as this voltage, okay, because they are in parallel, and we don't have current, we don't have a voltage drop. But at load we have current here, so this current is going to be this one plus this one, and this is very small current. IF is very small current, and the rest of the current is going to be determined by the R load, which is the load, resistance to the load, okay, or the impedance of the load. So this is all about our lecture today. We already explained let me just go back. We explained how the current is generated in a generator, and how we can get one direction of the current by using the commutator. And we explained that some types of the generators, which is separately excited, and the shunt self-excited generators. And we also mentioned very important lesson, which is armature reaction. So please make sure that you understand everything. If you couldn't understand my explanation, you can go to the link that I provide in this lecture. If I can go just to it. This is the link. You can just visit this link, and they will explain the movement of the DC generator, how it is moving, and how we can generate the voltage, everything. خلاص. Thank you so much for give me the time to explain the lesson to you. This is lecture 14 and 15, and this is the last lecture in our course. Thank you so much, and best wishes. Thank you.